Class. Okay, so another problem with electric fields where we have this object, it's like a line charge bent in the form of a semicircle, and there's like an insulating gap between it. So we have like a certain positive charge, say 4.7 microcoulombs on this top half, and the same amount of negative charge on the bottom half of this curved rod. And we want to find the electric field at point P. So this is a continuous charge distribution. Let's draw like an XY plane coordinate system. Okay, and so let's we should probably have a radius as well. Say the radius is 6 centimeters. So let's look at how we can find the electric field at point P. We're going to have to, do an integral, it looks like. So let's look at a little piece here that makes an angle let's say this angle here is theta, and we have this circular wedge here with a thickness d theta. So there's a certain amount of charge on this rod here that's essentially at the same angle theta. And this d theta, of course, is very small. And so the electric field due to this charge, dq, that would be dE, that would point in that direction there. Now, if we look at this same angle on this side, like this negative charge, we're also going to have a just go in this direction. So if we look at this part of the loop right here, electric fields point towards negative charges. So we're going to have a charge in that direction as well. Like for every point on the positive side, we're going to have an electric field this way. For every point on this negative side of the loop, we're going to have this symmetric electric field because the amount of charge in each portion is going to be the same. And so if we add up these two electric fields, let's say DE1, this is DE2, the x components are going to cancel out. And that's going to happen for every portion above the, say the x-axis is going to have a corresponding portion below the x-axis where the x components cancel out. So really what we need to, and the y components are going to be equal to each other. So what we really need to do is just, let's integrate across one quadrant. And just multiply by 2 to get the y component of the electric field. So like the electric field due to this dq1 and call this dq2. The y components are going to be identical from symmetry, and we have two charges, so we just add them up. So we get 2 times, let's say dEy is the y component of the electric field due to, say, the positive charge at that angle. And so we'll just integrate over one quadrant. where we need to find the y component of the electric field, which will of course depend on the angle. Then we integrate over 90 degrees, and then we're good. So that'll be the plan. And now I feel like I might have, well, we'll see if we can work with this picture here. Okay. So first off, dq is going to be lambda ds, where ds is the arc length. So like this segment here that goes through an angle d theta has a length ds. And so we have the charge density times the arc length, where lambda, that would be 4.7 microcoulombs. So let's just say q. Let's just look at going from here to here. That is a quarter of the circle. So the circumference of a circle is 2 pi r. So this would be pi r over 2. So lambda is 2q over pi r. So we know lambda. And ds, remember that arc length formula, S equals r theta. We'll use capital R to be consistent. So ds is r d theta. We want to integrate over theta. So here we have lambda r d theta. So we have like a charge per length times a length. D theta is dimensionless, so that'll give us a charge. And so the magnitude dE, let's say dE1. That'd be KE dQ over R squared. Okay, we can plug in dQ if we like. So we have lambda r d theta. We'll cancel out that r later. So that's dE1, and we want the y component of this. So like if this angle is theta, this angle is also theta. So the y component we would multiply by cosine of theta. So the y component, we have ke lambda. We're going to cross off the r now. So we'll have cosine of theta d theta over r. And let's multiply by 2. Because, that's just due to the positive charge. This negative charge is going to have an equal contribution. So let's just say dEy. Here we have 2 ke lambda cosine theta d theta divided by r. And now to get the the electric field overall, the y component of the electric field, we integrate over theta. Let's say theta equals 0 is here. Theta equals pi over 2. That'd be 90 degrees. So let's integrate for the y component of the electric field. So we take out these constants. Now we have 2 ke lambda over r. And then we just integrate cosine of theta d theta from 0 to pi over 2. And the integral of cosine of theta is just sine of theta, so that part's going to be easy. I'm going to do is I'm going to plug in lambda now. Lambda is 2q over pi r. Okay, we don't need this anymore. And then the integral of cosine theta is sine of theta. And again, sine of pi over 2, that's just 1, and sine of 0 is 0. So we have 4keq over pi r squared. Okay. And now it's a matter of plugging in the numbers. So I'm going to need a little room for this. So let's see. Well, it's recorded. You can always back up and see what you want. So I'm going to just write the result. Yeah, let's just get rid of this. Let's write the result here. So we have 4ke q over pi r squared. And let's plug in the numbers. I'm going to start down here. Yeah, let's get rid of this as well, just so we have room. Okay. So 4 over pi. We can just leave it as that for now. Ke, that is 9 times 10 to the 9th Newton meters squared over Coulomb squared. Q is 4.7 microcoulombs. So just write that. Micro is 10 to the minus 6. And then we divide by r squared. That would be 36 centimeters squared. Now let's write it a little more compactly, actually. So 6 centimeters, that's 6 meters over 100. And then we can square it instead of having to write out another conversion factor and square that. And actually the units work out very nicely. I'll just write the units up here. So we have Newton times meter times Coulomb. On the bottom we have Coulomb squared and then meter squared. So our units are going to be newtons per coulomb, which is what an electric field should be. Same as a volt times a volt over a meter. But let's do this. So on top we have 36 times 4.7 times 10 to the 13. Oh, interestingly enough, we're going to get some cancellation here. 6 squared is 36. And then we have pi times 10 to the 6 coulombs on the bottom. So obviously that cancels out. And this is going to be in scientific notation. 4.7 over pi. That's just a number between 1 and 9, or 1 and 10 really. Yeah, 1.50. And then 10 to the 13 over 10 to the 6 is 10 to the 7th power coulombs. So, yeah, just want to do a problem with a continuous charge distribution. So normally when you have like point charges, we have linear superposition. We know the electric field due to a point charge. And that'd be the magnitude of the electric field. But we can find the electric field due to an individual point charge, and then just add them all up using linear superposition. For a continuous charge distribution, this goes very simply to we consider a small charge dq at a particular location on our distribution, and then we just integrate over the distribution itself. So I want to practice both ways, just individual point charges and charge distributions. All right, and I think that'll be it for this one, and then I'll just do more in a separate video.